Welcome to Dataengineers Academy. Today we are going to discuss the query execution flow in BigQuery. Here is our roadmap for today. We will start with an architecture overview. Then dive into the core components including BOG, Colossus, and Jupyter. Finally, we will explore Dremel's execution stages, complete timeline, and key interview questions. Let's look at the example query we will use to trace the execution. We are selecting department and calculating total salary from a company employees table, filtering for recent hires, and grouping by department. The table has 10 million rows stored across 10 shards. Moving to section 1, the architecture overview. BigQuery is built on 4 core Google components. BOG manages compute. Colossus is the distributed file system. Jupyter is the massive network fabric. And Dremel is the execution engine. A key principle of BigQuery is that storage and compute are completely separated. Data lives in Colossus and never moves, while compute happens in Dremel. This enables infinite scaling without the need for indexes or capacity planning. Section 2 focuses on BOG, the cluster manager. Think of BOG as the operating system for Google's data center. It allocates compute slots, schedules workers near data, and handles fault tolerance seamlessly. When our query arrives, BOG allocates 500 slots, distributing them among leaf nodes, mixers, and a root server. If any worker fails, BOG instantly spins up a replacement so the query continues uninterrupted. Section 3 covers Colossus, the distributed file system. Colossus stores data in a proprietary columnar format called capacitor. It features independent compression, automatic sharding, and metadata statistics for efficient partition pruning. In traditional row storage, the entire row is read. But with Colossus's columnar storage, only the required columns are read. For our query, we only scan 3 out of 7 columns, saving a significant amount of disk I/O. This is the physical shard layout for our table. The 10 million rows are split across 10 shards. Unused columns are skipped entirely, meaning out of 900 megabytes of total data, only 330 megabytes are actually read. Colossus also leverages metadata for partition pruning. If a shard's maximum hire date falls before our filter criteria, the entire shard is skipped. This eliminates a million rows instantly without reading a single byte. Section 4 introduces Jupyter, the network fabric. Jupyter provides an astonishing 1 petabit per second bandwidth. It acts like a massive superhighway, ensuring that transferring data between Colossus and Dremel never becomes a bottleneck. Looking at the data flow over Jupyter, Colossus sends data to Dremel moving roughly 300 megabytes in just 10 to 15 milliseconds. Each active shard is transferred simultaneously to its corresponding leaf node. To put Jupyter's speed into perspective, transferring 300 megabytes takes 24 seconds on home Wi-Fi, but under 3 milliseconds on Jupyter. This makes remote storage feel as incredibly fast as a local disk. Section 5 dives into Dremel's leaf nodes. These are the parallel workers at the very bottom of the execution tree. Each leaf node reads one shard, applies filters, performs partial aggregations, and sends results up. For our query, 9 leaf nodes operate in parallel. Each node reads its assigned chunks, filters out old rows, and aggregates the remainder. What started as 1 million rows per shard is quickly reduced to just 5 rows. Section 6 explores Dremel mixers. Mixers sit between the leaf nodes and the root server. Their primary job is to aggregate the partial results, preventing the root server from being overwhelmed by massive amounts of data. Mixers are essential for data reduction. They take thousands of partial rows from leaf nodes and combine them into a small summary before passing them up. This two-phase aggregation is the secret to massive scalability. Here is the mixer tree for our specific query. Mixer 1 aggregates results from leaves 1 through 5, while Mixer 2 aggregates leaves 6 through 9. They act like supervisors summing up local totals. Mixers handle various operations. For sum and count, they add partials. For min and max, they find extremes. For count distinct, they use approximate hyperlog sketches to merge data efficiently at scale. Section 7 covers the Dremel root server. Acting as the coordinator, the root server receives the SQL query, creates an optimized execution plan, and dispatches sub-plans to the workers within mere milliseconds. In the final phase, the root server receives the combined results from the mixers, merges them into the final 5 rows, formats the output, and returns the result back to the user. Section 8 shows the complete execution timeline. Scanning 10 million rows takes roughly 82 milliseconds. From parsing the query to allocating bog slots and aggregating results, hundreds of steps happen in perfect harmony. This chart shows the massive data reduction at each stage. Through column pruning, shard pruning, and multi-stage aggregation, BigQuery reduces 900 megabytes of raw data down to just 500 bytes of output. Section 9 brings us to our key takeaways. Remember, Bog manages resources, Colossus stores data, Jupyter provides the network, and Dremel executes the query using a tree of leaf nodes, mixers, and a root server. BigQuery achieves its speed through massive parallelism, columnar storage, and separated compute and storage layers. However, be cautious with select star queries, as they force full table scans and increase costs. Here are some top interview questions. You should know that BigQuery's speed comes from Dremel and Jupyter. Colossus uses the capacitor columnar format, and Bog handles automatic fault tolerance. Continuing with interview questions. Remember that predicate pushdown filters data early. Multi-stage aggregation handles massive group Bs. And BigQuery differs from Snowflake by using serverless slots instead of virtual warehouses. Thank you for watching this complete guide on BigQuery execution flow. We hope this deep dive helps you in your data engineering journey with Data Engineers Academy.